Good morning, myself Avijit Routh, Assistant Professor of the Institute of Technology in Electrical Engineering Department. Today I'll discuss some basics of electric field and electric potential. So initially, if I'll consider a point charge Q, and due to this point charge, what is the electric field at a distance R? The value of electric field E at a distance R, E equals to 1 by 4 pi epsilon naught. This is arbitrary constant into Q by R square. Basically, electric field is directly proportional to charge and inversely proportional to the square of the distance for a point charge. The inside of electric field is nothing but the number of flux line passing through unit area. So if I'll assume this is a point charge, so for a positive charge, the field lines are always radially outward direction, and for negative charge, the field lines are always inward direction. So if I'll consider a small portion very close to the plus charge Q, the number of flux line is more compared to if we'll consider the same area away from the point charge. That's why the electric field is decreasing with increase of the distance. Simultaneously, for a charge, if I increase the number of charge over there, the number of flux line will be increasing and the value of electric field will be increasing. Now, instead of a point charge, if I'll consider a infinite wire with a charge density lambda coulomb per meter, then what will be the electric field at a distance r? So before start this topic, first you try to understand. If I'll consider this is a infinite wire and there is a lots of charge over there, so when I'll calculate the electric field at that point, there will be an effect over there for individual charges. So that's why it is very difficult to take any of the charge and calculate what is the electric field individually. So that's why if I'll consider from center to a distance x a small elementary part, that is dx, then try to calculate what is the electric field at point O due to the small elementary length dx. So I know lambda coulomb charge per meter. So within the length dx, the charge will be lambda into dx, and I can consider this charge is nothing but dq. And due to this charge dq, what is the electric field at that point O? Using this formula, okay, I'll make this is basically a vector quantity. So for a point charge plus q, the electric field is radially outward direction, so I can put the direction is r cap. So for this elementary part dx, the total charge is dq, and what is the electric field at that point O? So basically I have to calculate what is the distance, and this distance is nothing but root over of x square plus r square. I can easily calculate using Pythagoras theorem. Now at that point O, the electric field due to the small elementary part dE, that should be equals to 1 by 4 pi epsilon naught lambda into dx, basically the charge dq, by distance square, and distance square is x square plus r square. But the point is that the electric field is always outward direction, so for this positively charged, so this is the value of dE. Similarly, if I'll take a symmetrical portion over there, and for this dx, the electric field will be also acting along this direction. So now if I'll split this dE into two components, if I'll consider this angle is theta, so this is also theta, So this component will be your dE cos theta, and this component becomes your dE sin theta. Similarly, if I'll split this component also, similarly this is theta, this is theta. So this component is dE cos theta, and similarly this component is dE sin theta. So basically, if I just added up these two parts, all the sine component are cancelled and only the remaining component is the dE cos theta. So if I'll consider this is an infinite wire, and if I'll split into a small segment, so all the sine component basically cancelled and the effective component is the dE cos theta. So that's why the electric field, the effective electric field, I can write the effective electric field is dE cos theta, and this value equals to 1 by 4 pi epsilon naught lambda into dx by x square plus r square into cos theta. Now what is the value of cos theta? I can easily calculate, that is 1 by 4 pi epsilon naught lambda into dx by x square plus r square. If I consider this is theta, so obviously this is my base and this length equals to r, so I can write r by root over of x square plus r square. Okay. Now when I'll calculate the total electric field, so the total electric field, that basically 1 by 4 pi epsilon naught lambda into r integration of dx by x square plus r square to the power of 3 by 2. And what will be the limit? If I'll consider this is 0, 0, so this point basically, if we are talking about an infinite where this is minus infinity, this point is plus infinity, so the limit will be your minus infinity to plus infinity. So I can also write that is 2 lambda r by 4 pi epsilon naught 0 to infinity dx by x square plus r square to the power of 3 by 2. So now if I'm able to integrate this portion, this is simple mathematics. So you can take you can take a relation between x and r. What is the relation between x and r? So this is theta, so this is base, this is height. So height by base, so that is x by r, basically your tan theta, or you can write x equals to your r tan theta. Now if I'll take the derivative with respect to theta, so dx equals to r sec square theta into d theta. So if I'll go for this integration, that is integration of dx, so dx I can write r sec square theta d theta, and this portion becomes your x square plus r square. So x square means r square tan square theta plus r square to the power of 3 by 2. And at the same time I have to change the limit also, because x equals to r tan theta. So what is the lower limit of x? The minimum value of x equals to 0. Based on that I can write the lower limit of theta equals to 0. And what is the maximum limit of x? The maximum value of x equals to infinity. So when I'll put x equals to infinity, I'll get theta equals to 90 degree, or I can write that is pi by 2. So now I can write 0 to pi by 2 r sec square theta, sorry I'm making a mistake, that is d theta, sec square theta d theta. This is 1 plus tan square theta, that is sec square theta to the power of 3 by 2. So the final result is r cube into sec cube theta. So finally I can conclude that is 1 by r square 0 to pi by 2 cos theta into d theta, and the integration of cos theta d theta is sin theta, and if I'll put the limit, finally the result becomes your 1 by r square. So if I'll put this result over here, I'll get 2 lambda r by 4 pi epsilon naught into 1 by r square. And if I'll see the figure, all the electric field, the entire electric field is acting along this direction, and this is nothing but the radial direction. So I can write this is basically r cap. So finally I can conclude the electric field is lambda by 2 pi epsilon naught into r along r direction. So there is a difference. When I'll take a point charge, the electric field is 1 by 4 pi epsilon q by r square. So basically the electric field is directly proportional to, inversely proportional to r square. But when I'll take a infinite long wire conductor, so that time the electric field is proportional to 1 by r. Okay. Similarly, instead of a infinite wire, if I'll consider a infinite metallic sheet, that time the result is little bit different. If I'll consider a infinite metallic sheet, and if I'll consider the charge density is sigma coulomb per meter square, then what will be the electric field at any height h? So here if I'll consider this is a height h, now there is a lots of charge, so that's why if I take a small elementary part and first try to calculate what is the electric field for this small elementary part, and then using integration I can able to calculate what is the net field at a height h. So initially if I'll consider the radius is x and the depth is dx, so what is the area? The area is very simple. The area is 2 pi x into dx. And if I'll consider, already I'll consider the charge density is sigma coulomb per meter square. So total charge dq within this small segment will be sigma into 2 pi x into dx, that is dq. And for this charge, what is the electric field? See, everywhere this distance is same. If I'll consider from there or if I'll consider from there, everywhere the distance is same. And if I'll consider this is x and this is h, so obviously this distance becomes your root over of x square plus h square. So now I calculate what is the electric field. The electric field D equals to 1 by 4 pi epsilon naught dq, and the value of dq equals to sigma into 2 pi x into dx by distance square, and distance square is nothing but x square plus h square. But there is the same type of problem if I'll consider two symmetrical part. If I'll consider this is theta, so obviously for this small segment the electric field will be acting along this direction, and for this small elementary part the electric field will be acting along this direction. So if this is theta, obviously this is theta, so this component will be dE cos theta and this component will be dE sin theta. Similarly, if I'll split this section also, here I'll get dE sin theta and this portion becomes your again dE cos theta. So again I can understand if I'll added up all the small segment, then all the sine component basically cancelled and the remaining component will be the cos component. So the effective value is nothing but dE cos theta, and that is basically acting in z direction if I'll consider this is xy plane. So all the charges placed in xy plane, so overall electric field will be acting along z direction. So what is the value of dE cos theta? The value becomes 1 by 4 pi epsilon sigma into 2 pi x into dx by x square plus h square. And what is the value of cos theta? So if I'll consider this is theta, so this is my base, so height is h, so h by x square plus h square to the power of half. So ultimately, when I'll calculate the net electric field in it, I have to integrate. So which are the sigma 2 pi h by 4 pi epsilon naught, all are the constant. So here there should be x dx by x square plus h square to the power of 3 by 2. And the x is varying if I'll consider infinite metallic sheet. So the radius will be varying from 0 to infinity. So if I'll integrate this result, finally I'll get that is sigma by 2 epsilon naught. Okay, simple integration. After doing the integration, and the direction will be, if I'll consider this is xy plane, this is n cap. N cap basically define the direction is along z direction. If I'll consider this is xy plane, the electric field will be z direction, and it is not an xy plane, any arbitrary plane, so the direction of the electric field will be perpendicular with the plane. Okay, so after all, if you'll conclude the three results for a point charge, what I'll get, the electric field at a distance equals to 1 by 4 pi epsilon naught into q by r square along r direction. And I'll conclude a infinite where that time the electric field and charge is equally distributed, that is lambda coulomb per meter. So that time the electric field will be lambda by 2 pi epsilon naught into r. Okay, this is the electric field at a distance r. And instead of a infinite where, if I'll take a infinite metallic sheet and charge density is sigma coulomb per meter, at any height the electric field, the result is sometimes looking strange, sigma by 2 epsilon naught, it is independent of the height. Any height you'll get the same amount of result. So from this beginning lecture, you can understand the how electric field is varying from point charge for a one-dimensional infinite wire and for a two-dimensional metallic sheet. So in my next session, I'll discuss how electric field and electric potential are relate with each other, and how to make some relationship between electric field and electric potential. Sometimes to solve the numerical problem in electric field theory, it is easier to calculate the potential. Basically potential is a scalar quantity, and sometimes you feel some difficulties when to solve the problem to calculate the electric field. Basically the electric field is a vector quantity, and there is a one relationship between electric field and electric potential. And next class I'll discuss this remaining part. Thank you.